This is lecture 10, Conveyor Models, part 1 for IE 4355 Facilities Planning. The material discussed in this lecture is also covered in section 10.8 of your textbook for this class. As always, we start our lectures or our new topics with the course objectives and how they are linked to our lecture. So in this particular lecture, the first objective for this course, which is to develop an understanding of principles of facility location, layout, material handling systems, and to practice design facilities or designing facilities, is the objective that is tied to this lecture. Specifically, we are going to be looking at the material handling systems aspect by focusing on the conveyor models. So the lecture or the agenda for this lecture includes an introduction to the topic. Again, we're going to be focusing on material handling systems, specifically for conveyors. And we are going to look at two different types of problems. The first problem is the deterministic problem for conveyors that have loading and unloading sequences that are deterministic. And then in part 2 of this lecture, which is the next video, we're going to cover the conveyor loop with Poisson arrivals, which means that we have some uncertainty in the arrival of the items that are going to be using the conveyors. So the learning objectives for this lecture are to learn models for specific type of conveyors and to understand the basic procedures for calculating horsepower requirements for power belt and roller conveyors. So as an introduction, fixed path material handling systems are among the most used or widely used material handling systems. You saw in our previous lectures that we discussed different type of material handling equipment. So out of those that we discussed, the fixed path material handling systems are the ones that are most widely used in terms of material handling system for warehouses and industry. They include material handling equipment such as power belt and roller conveyors, trolley conveyors, and similar conveyors with discrete carriers, and automated guided vehicles. The models we present in this lecture provide some basic procedures for the design or analysis of various types of fixed path material handling systems, just like the ones that we are showing in these two pictures. So let's look at the trolley and similar conveyors with discrete carriers or carriers. We present two types of models for conveyors with discrete carriers, such as trolley conveyors. And these are the pictures. So you have the conveyors moving around and you see that they have a limited capacity in terms of the number of items that you can put in each one of those carriers. So you see in the left side of the slide, this picture in which you can put a single box in each one of the carriers. And then on the picture on the right, you have these big boxes in which you can put multiple items. But still, you still have a limitation in terms of space. So the first model is a deterministic model, which means that we know from the beginning, we know when the items or that we're going to put in these conveyors are going to arrive. So we know they're going to arrive at time 1, time 2, time 3, and so on. We focus on the analysis of closed loop, unidirectional, recirculating conveyors with discretely spaced carriers. Conveyor analysis was developed because of a number of operating problems that occur with trolley conveyors, namely, first, at a loading station, no empty carriers were available when a loading operation was to be performed. And second, at an unloading station, no loaded carriers were available when an unloading operation was to be performed. So these are two reasons why this conveyor analysis was developed. Conveyors provide many of the links among workstations or work areas in modern production and distribution systems. Some conveyors are used basically as a transport system. Some are used for storage or accumulation purposes, while others support both transport and storage functions. Sortation conveyors are also used extensively by companies that move parcel packages and mail. I mentioned in some of the videos, some of our previous videos, like companies such as UPS, Amazon, FedEx, they use these sortation conveyors to distribute the items. For example, if you are in a warehouse and you have an X amount of trucks waiting for transportation purposes, then you will have these trucks parked in the right location, and the sortation conveyor will use sensors to distribute the items or the packages that will go to each one of the trucks. A conveyor system basically consists of one, the conveyor equipment, two, the loading and unloading stations, and three, the operating discipline or computer control employee. System design parameters includes equipment parameters, such as the speed of the conveyor, waiting space allowance for incoming and outgoing loads, and three, the number, spacing, and sequencing of loading and unloading stations around the conveyor. So these are the system parameters when we are considering the design of a conveyor or to study the performance of a conveyor. We need to know the equipment parameters, such as the speed of the conveyor, the waiting space allowances for incoming or outgoing loads, and the number, spacing, and sequencing of loading and unloading stations around the conveyor. The principles to be used in designing closed loop unidirectional conveyors are the following. First, the uniformity principle. Materials should be uniformly distributed over the conveyor. Two, the capacity principle. The carrying capacity of the conveyor must be greater than or equal to the system throughput requirements. And three, the speed principle. The speed of the conveyor, which is measured in number of carriers passing by a fixed point per unit time, must be within the permissible range defined by loading and unloading station requirements and the technological capability of the conveyor. So three important principles: uniformity principle, capacity principle, and the speed principle. So let's look at this specific case for designing conveyors. So the case that we're going to study in this video is the conveyor loop with deterministic loading and unloading sequences. So conveyor loop with deterministic loading and unloading sequences. So this is the example or the illustration show the problem. This is the schematic representation of the recirculating conveyor. As you can see by number, 1, 2, 3, 4, 5, 6, 7, and then you have S-2, S-1, S. Those are the workstations. And then, so those circles around the, around or inside the rectangle with numbers, those are representing the workstations. And then that line with dots, those are representing the carriers for and the conveyor. So those carriers are discretely spaced. So they have the same space between them, and they are moving at a specific speed around the workstations, and they have a specific direction. Okay, so in this case, they're going counterclockwise. So there are S stations located around the conveyor. They are numbered in reverse sequence to the rotation of the conveyor. Each station can perform loading and or unloading for the conveyor. There are K carriers equally spaced around the conveyor, and the passage of a carrier by a workstation establishes the increment of time used to define material loading and unloading sequences. So if we use station 1 as a reference point in defining time, so we are going to use station 1 as that point to defining time. Consequently, carrier N becomes carrier N plus K immediately after passing station 1. Because there are K number of carriers. The sequence of points in time at which a carrier passes station 1 is denoted by Tn, where Tn is the time at which carrier N passes station 1. The amount of material or number of items loaded on carrier N as it passes station I is given by this function f of I of n, for I equals 1, 2, up to S. So remember S, I is the station, and we have S number of stations. The amount of material carried by carrier N immediately after passing station I is denoted by HI of N. Each carrier may hold multiple items. So for steady state operation, total amount of material loaded on the conveyor must equal the total amount of material unloaded. Since it is assumed that the conveyor will be operated over an infinite period of time, the sequences f of I and of n are assumed to be periodic with period p. Thus, fi of n is going to be equal to f of I of n plus p, which is the period. Additionally, the summation from n to p and from I to S of f of I of n is going to be equal to 0 because of the requirement that all material loaded on the conveyor must be unloaded. In analyzing the conveyor, it is convenient to employ the following relation. Capital F of 1 of n is going to be equal to the summation from 1 to station I to S of f of I of n. And we obtain the following result. K over P cannot be an integer for steady state operations. Letting R equals K mod P, R over P must be a proper fraction, meaning that the top number less than its bottom number for general sequences f of 1 of n to be accommodated. So it is desirable for p to be a prime number. Now the operation r equals k mod p means r is given by the remainder following the division of k by p. So 12 mod 7 is going to be equal to 5, and 26 mod 8 is going to be equal to 2. The materials balance equation for carrier n can be given as h1 of n is going to be equal to h1 of n minus r plus f1 of n. In order to determine the values of hi of n, the following approach is taken. We let h1 star of n be a particular solution to equation 1 and use the recursion h1 star of n equal to h1 star of n minus r plus f1 of n by letting h1 star 1 equal to 0. Given hi star n of n, the value of hi plus 1 star of n is obtained from the relation h hi plus 1 of star of n is going to equal to hi star of n minus fi of n. And given this hi star of n for I equals 1 up to s, we let c equals the minimum of in for hi star of n. The desired solution is given by hi of n equals hi star of n minus c. And the required capacity per carrier in the conveyor is going to be equal to B, which is equal to the maximum of In of hi of n. So let's look at one example. I know those were a lot of equations. So let's put this into practice. So to illustrate the deterministic solution procedure, consider the situation involving a single loading station and a single unloading station. And those are looking, those stations are, the loading station are station 1 is station 1, and then the unloading station is station 2. And then you have the conveyor going around. The conveyor has 9 carriers, K, equally spaces. Determine the required capacity per carrier. That's our goal. The loading and unloading sequences occur with the period of P equals 7, and they are given as follows. So for 1, which is this loading station, you have the 7 periods, so you have 7 numbers. So f of 1, f1 of n is that set. Is giving you those 7 numbers, 1, 1, 2, 2, 2, 1, 1. So if you look at the total, if you sum 1, 1, 2, 2, 2, 1, 1, that is equal to 10. And then f2 of n is for the unloading station. So in the first period, there's nothing to unload. So 0, 0, 0, 0, 0, up to the 6 and 7 period in which the unloading station is going to unload 5 and 5. So that's our sequence with the period of P equals 7. So if we use the definition of F1 of n, then we can find our, so you're going to subtract f of 1 of n minus f of f2 of n. for each period. So that's how you get 1, 1, 2, 2, 2, -4, -4. And if you look for R is going to be equal to K mod P. So K is 9, which are 9 carriers, and mod 7, which is the period. So 7 is the period. So 9 mod 7 is equal to 2. Note that K over P is 9 over 7 is not an integer. R over P is equal to 2 over 7, which is a proper fraction, and P equals 7 is a prime number. Recall the amount of material carried by a carrier N immediately after passing station I is denoted by HI of N. Arbitrarily, we let HI star of 1 equal to 0 and employ the relation H1 star of N equals H1 star of N minus R plus F1 of N to determine H1 star of 3 as follows. H1 of star of 3 is equal to H1 star of 1 plus F1 of 3, which is going to be equal to 0 plus 2, which is equal to 2. Recall the amount of material carried by carrier N immediately after passing station I is denoted by HI of N. So arbitrarily, we let HI star of 1 equal to 0 and employ the relationship again to determine H1 star of 3 as follows. So that's what we show on the previous slide. Likewise, we can do H1 star of 5, which is going to be equal to the result of the previous equation, H1 star of 3 plus F1 of 5, which is going to be equal to 2 plus 2 is equal to 4. And since R equals 2, the next computation is for H1 star of 7. So H1 star of 7 is going to be equal to H1 star of 5 plus F1 of 7, which is going to be equal to 4 minus 4, which is equal to 0. The next one is H1 star of 9. However, since P is equal to 7, period is 7, H1 star of 9 is going to be equal to H1 star of 2. Hence, H1 star of 2 is going to be equal to H1 star of 7 plus F1 of 2, which is equal to 0 plus 1 is equal to 1. Likewise, H1 star of 4 is going to be equal to H1 star of 2 plus F1 of 4 is equal to 1 plus 2, which is equal to 3. And then H1 star of 6 is going to be equal to H1 star of 4 plus F1 of 6, which is equal to 3 minus 4, which is equal to minus 1. Hence, H1 star of N, that set, we have computed all the values, is equal to 0, 1, 2, 3, 4, minus 1, and 0. The values of H2 star of N are obtained using the relation H2 star N equals H1 star of N minus F1 of N. Therefore, H2 star of N is equal to this difference for the set that we just generated for H1 star of N minus F1 of N. And that's H2 star of N set is equal to minus 1, 0, 0, 1, 2, minus 2, minus 1. The value of Z is found to be the minimum of that set. Okay, so H1 star of N equals minus 2. For I equals 2 and N equals 6. Consequently, the sequence HI of N are given by H1 of N equals 2, 3, 4, 5, 6, 1, and 2. H2 of N equals 1, 2, 2, 3, 4, 0, and 1. And B, which is the capacity of the carrier, is going to be equal to the maximum of those two sets. And the maximum is equal to 6 for I equals 1 and n equals 5. Therefore, each carrier must have sufficient capacity to accommodate 6 items. Okay, so I'm going to conclude the lecture for this video with this example. On part 2, we're going to look at the conveyor loop with Poisson arrivals. There's the example that we just discussed. We were able to find the maximum capacity for a conveyor for conveyor loops with deterministic loading and unloading sequences. So the methodology presented in this lecture will allow you to compute that capacity. Okay, so on the next video, we're going to cover conveyor loop with Poisson arrivals.